Most diesel enthusiasts can rattle off specs for the 8V92 or debate the merits of the legendary Series 71, but ask about the 20V149 and you'll get blank stares from everyone except a handful of marine engineers and oil field veterans. This wasn't an engine for highways or construction sites. It was Detroit Diesel's answer to a question most people didn't know existed. What happens when you need nearly 3,000 horsepower running continuously for days in the middle of the ocean? The 20V149 represented the absolute peak of Detroit's two-stroke philosophy pushed to its mechanical limits. With 48.8 liters of displacement spread across 20 cylinders, 3 superchargers, 6 turbochargers, and fuel consumption measured in hundreds of gallons per day, this engine existed in a rarefied world where normal engineering constraints didn't apply. This is the story of an engine so extreme that even Detroit Diesel struggled to find customers who could handle it. By the mid-1960s, Detroit Diesel dominated the two-stroke market with proven platforms. The Series 71 had become legendary in buses and trucks since its 1938 introduction. The Series 92, launched in 1974, offered more displacement for heavier applications. These engines succeeded because they delivered power density that four-stroke competitors couldn't match while remaining serviceable in the field with basic tools and minimal downtime. But a problem was emerging in specialized industrial sectors that Detroit couldn't ignore. Oceangoing tugboats needed more sustained power than existing engines provided for moving increasingly larger container ships through congested harbors. Offshore drilling rigs operating in deeper waters required continuous high-output engines that could run for weeks between maintenance intervals while powering complex drilling operations. Industrial pump stations responsible for flood control or moving millions of gallons daily needed power plants that traditional engines simply couldn't deliver without installing multiple units. The gap wasn't just about peak horsepower numbers on a specification sheet. These applications required massive torque at moderate RPM, maintained continuously under extreme loads in harsh environments. A truck engine might produce impressive numbers for short bursts during acceleration or hill climbs, but marine and industrial customers needed engines that could hold near maximum output for days or even weeks without overheating, component failures, or requiring shutdowns for anything beyond routine checks. Detroit's existing platforms had reached their scaling limits. The Series 71, though revolutionary when designed in the 1930s, couldn't grow much larger without fundamental redesigns. The Series 92 offered more displacement, but still fell short of emerging industrial power requirements. Competitors like Caterpillar and Cummins were developing larger four-stroke engines, threatening Detroit's dominance in high-output applications. Rather than abandoning their proven two-stroke design, Detroit engineers decided to scale up dramatically. The Series 149 was born from this decision. Named for the 149 cubic inches displaced by each cylinder, this platform nearly doubled the per-cylinder displacement of the Series 71 and exceeded the Series 92 by over 50%. The Series 149 wasn't just bigger cylinders bolted together. Detroit maintained their core design philosophy: uniflow scavenging through Roots superchargers, unit fuel injectors per cylinder, and individual cylinder heads for field serviceability. These choices preserved the engineering DNA that made Detroit engines reliable while scaling up to unprecedented power levels. The first production variant, the 12V149, arrived in 1966. With 12 cylinders in a 60-degree V configuration, it delivered substantial power increases over anything Detroit had previously offered. Marine customers immediately recognized its potential. Tugboat operators and commercial vessel owners began specifying 12 V149s for new builds and repowers. The 16 V149 followed in 1974. Adding 4 more cylinders and expanding both power output and market reach. Both versions featured modular construction with individual cylinder heads, allowing mechanics to service specific cylinders without disassembling entire engine banks. This design philosophy proved critical for offshore and remote installations where specialized facilities didn't exist. But some customers needed even more. That's where the 20V149 entered the picture. The Detroit Diesel 20V149 wasn't evolutionary, it was revolutionary in scale. Total displacement reached 2,980 cubic inches or 48.8 liters. To put that in perspective, a modern heavy-duty truck engine typically displaces 12 to 15 liters. The 20V149 was more than 3 times larger. The architecture used a unique 3-block design, 2 6-cylinder banks flanking a central 8-cylinder section. This wasn't simply doubling a 10-cylinder engine or adding cylinders to an existing design. The composite construction allowed Detroit to use existing manufacturing tooling while adapting their proven block castings and machining processes, keeping development costs manageable despite the engine's massive scale. More importantly, it made the enormous engine more serviceable in the field. Each section could theoretically be worked on independently, absolutely critical for installations where pulling the complete engine was physically impossible due to space constraints or the sheer logistics of moving a multi-ton power plant. The traditional 60-degree V-angle preserved balance and smoothness despite the enormous displacement and cylinder count. Each cylinder measured 149 cubic inches with a perfectly square bore and stroke of 5.75 by 5.75 inches. This square configuration wasn't arbitrary. It provided uniform combustion characteristics and consistent power delivery across all 20 cylinders, absolutely essential for the sustained high-load operation these engines would face in continuous duty applications, where even slight cylinder-to-cylinder variations could cause vibration or uneven wear patterns over thousands of operating hours. Compression ratios ran 17:1 for naturally aspirated versions and 16:1 for turbocharged variants. Being a 2-stroke, every crankshaft revolution produced a power stroke from every cylinder. This meant 40 power pulses per revolution compared to 10 from an equivalent 4-stroke V10, explaining the engine's distinctive sound and incredible power density. Managing airflow for 20 cylinders firing every revolution required extreme solutions. The 20V149 used 3 Roots-type superchargers working in concert to scavenge exhaust gases and fill cylinders with fresh air. 6 turbochargers supplemented the superchargers, maintaining intake pressure under load and improving overall efficiency. Intercoolers reduced intake temperatures, preventing detonation and improving power output. Fuel delivery used 20-unit injectors, 1 per cylinder, mechanically actuated by the camshaft. Despite the mechanical complexity of timing 20 injectors, Detroit's proven unit injector design ensured precise fuel metering. A governor system balanced power output with engine load, maintaining consistent performance as demands varied. Thermal management became a massive engineering challenge. Cooling 20 cylinders producing nearly 3,000 horsepower required dual water pumps circulating coolant through all 3 blocks. Heat exchangers and auxiliary coolers were standard, with specific configurations varying by installation environment. Marine applications often used seawater cooling systems. Land-based installations required massive radiators. Lubrication relied on a wet sump system with high-volume oil pumps. Oil coolers and extensive filtration ensured the lubrication system could handle continuous operation at maximum load. Oil capacity measured in dozens of gallons, and oil change intervals required hundreds of gallons of fresh lubricant. The noise was legendary. With 20 cylinders firing every revolution, exhaust pulses created sound pressure levels that required extensive baffling in enclosed spaces. Marine engine rooms needed special insulation. Pump stations required acoustic treatment to protect workers. The exhaust note wasn't just loud, it was physically felt as much as heard. Emissions predated modern standards entirely. The 20V149 produced unburned hydrocarbons, particulate matter, and nitrogen oxides at levels that would never meet today's regulations. This wasn't a design flaw. Environmental regulations simply didn't exist when the engine was developed. Despite its immense size, Detroit maintained field serviceability. Individual cylinder heads allowed mechanics to work on specific cylinders without major disassembly. Inspection ports provided access to critical components. Many parts shared compatibility with other Detroit engines, simplifying logistics for customers operating mixed fleets. Performance numbers were staggering. Turbocharged and intercooled versions peaked over 2,900 horsepower with torque exceeding 7,000 pound-feet. Rated speed typically ran around 1,800 RPM, well below what the engine could theoretically achieve. Lower continuous speeds prioritized durability and efficiency over peak output. Fuel consumption was measured in hundreds of gallons per day at full load. This engine wasn't efficient by modern standards, but efficiency wasn't the priority. Continuous reliable power was everything, and fuel costs were secondary to uptime in the industries that used these engines. The 20 V149 never powered highway trucks or city buses. Its applications existed at the extreme end of industrial power requirements, where only the largest, most durable engines survived. Marine installations represented the engine's primary market. Large tugboats moving ships in harbors needed sustained high torque at moderate RPM for hours. Commercial fishing vessels operating in open ocean required reliable power far from shore. Dredgers moving material from harbors and waterways ran these engines continuously for days. Detroit's two-stroke design provided power density advantages over four-stroke competitors. Higher output came from smaller, lighter packages, critical when engine room space was limited. Many vessels installed twin 20 V149s for redundancy and total power, with each engine capable of moving the ship independently if one failed. Gear reduction systems converted engine RPM into usable propeller thrust. Some installations used transmissions specifically engineered around the 20 V149's torque characteristics, optimizing efficiency across the engine's operating range. Offshore support vessels servicing drilling rigs also adopted the 20 V149. These ships needed reliable power for station keeping in rough seas while transferring personnel and equipment. Engine reliability was literally life-critical in these applications. The oil and gas industry became another major customer. Hydraulic fracturing required massive pumps injecting fluids into underground formations at extreme pressures. The 20 V149's combination of high continuous output and proven reliability made it ideal for fracking operations running around the clock in remote locations. Mounted on mobile skids or enclosed trailers, these engines powered pumps and compressors in some of the harshest environments imaginable. Dust, extreme temperatures, and continuous maximum load operation tested every component. The ability to perform major maintenance in the field without specialized facilities proved invaluable. Industrial pumping applications also utilized the 20 V149. Flood control systems in vulnerable regions used multiple engines driving pumps capable of moving millions of gallons hourly. Agricultural irrigation in areas lacking electrical infrastructure relied on these engines to move water across vast distances. Generator sets represented another niche application. These weren't residential backup generators. They were mission-critical power systems for mining operations, remote construction projects, and emergency infrastructure. Some were even installed in hardened facilities during the Cold War as part of civil defense planning. With adequate fuel and maintenance, these generators could run indefinitely, providing stable power regardless of external conditions. Reliability mattered more than efficiency when an entire facility depended on continuous electricity. There were experimental applications in locomotives and specialized mining equipment, but these remained prototypes or limited builds. The engine's weight, emissions, and fuel consumption made it unsuitable for most mobile land applications, especially as emission regulations tightened through the 1980s. Custom integration was standard practice, not the exception. Detroit supplied base engines from their factory, but final installations were configured by specialized integrators like MTU, Allison Transmission, and dedicated marine engineering firms. Each application required bespoke cooling systems designed for specific water temperatures and quality, custom air filtration tailored to operating environments ranging from salt spray to oil field dust, and control panels integrating with vessel or facility systems. Maintenance requirements were intensive and non-negotiable. Filters needed changing on strict schedules measured in operating hours. Injectors required periodic testing and calibration to maintain proper fuel delivery across all 20 cylinders. Turbochargers demanded regular inspection for bearing wear and shaft play. Cooling systems needed constant monitoring for leaks, corrosion, or blockages that could cause localized overheating. This wasn't equipment you could neglect and expect to keep running. Fuel consumption made the engine economically viable only in specific industries where uptime and power output mattered infinitely more than operating costs. In marine applications where vessel day rates exceeded tens of thousands of dollars, fuel costs were minor compared to the revenue loss from engine failures. In oil field operations where production delays could cost millions, keeping pumps running justified any fuel expense. Noise and emissions further restricted use to industrial settings far from populated areas or environments with strict environmental controls. But in appropriate applications with proper maintenance, the 20 V149 was nearly indestructible. That's why decades later, some still operate in marine facilities, oil fields, and critical infrastructure installations. By the early 1990s, the 20 V149's era was ending. This wasn't failure, it was obsolescence driven by changing technology and regulations. Environmental regulations became the primary driver. The EPA's increasingly strict emission standards targeted exactly what made two-stroke diesels powerful. Unburned hydrocarbons, particulate matter, and nitrogen oxides all exceeded allowable limits. Retrofitting the 20 V149 for even early Tier 1 standards was economically and technically impractical. Competition intensified simultaneously. Cummins, Caterpillar, MTU, and Volvo introduced efficient four-stroke engines with electronic fuel injection and digital management. These engines produced comparable power while consuming less fuel, generating less noise, and running cleaner. Lower maintenance requirements appealed to cost-conscious operators. The 20 V149 relied on mechanical injectors and analog governors. Reliable and proven, yes, but technologically outdated. Modern engines offered capabilities the 20 V149 couldn't match. Real-time diagnostics, electronic power management, and emissions controls. Demand evaporated. Detroit quietly discontinued the Series 149 line, and the 20-cylinder variant disappeared from production. Many existing units were retired and replaced with modern power plants meeting new regulatory requirements. But the 20 V149 never truly died. Among marine engineers, veteran mechanics, and diesel enthusiasts, it achieved legendary status. The deep, rhythmic rumble of 20 cylinders at idle was unmistakable. Those who'd worked with these engines didn't just remember the specifications, they remembered the experience. Enthusiasts seek out surviving units for restoration. Diesel shows, collector exhibitions, and YouTube channels dedicated to heavy equipment occasionally feature working 20V149s. Restoration isn't easy. Parts availability requires salvaging components from derelict engines or custom machining replacements. Some 20V149s remain in active service. Pump stations, generator facilities, and dry docks still operate engines that never received upgrades because they still work. These engines often run only during peak demand or emergencies, but they always start when needed. What makes survivors impressive is their age. Many are operating decades beyond intended service life. Detroit didn't design the 20 V149 to last 50 years, yet some units approach that milestone with proper maintenance. This longevity testifies to both build quality and the dedication of mechanics who maintain them. In diesel engine history, the 20 V149 occupies a unique position. It represents the pinnacle of Detroit diesel's mechanical era, the absolute limit of two-stroke scaling before electronics and emissions regulations changed everything. It was never meant for mass production or widespread adoption. It solved specific problems for customers with extreme power requirements and the resources to maintain such machines. For those who understand its context, the 20 V149 wasn't excessive or impractical. It was precisely engineered for applications where nothing else sufficed. That specialized excellence, combined with legendary reliability in appropriate applications, earned it a permanent place in diesel history. The engines may be rare and largely forgotten outside specialized circles, but their legacy endures wherever extreme power requirements meet mechanical simplicity and proven durability.